Okay, so this is continuing our little introduction to matrices and Gauss-Jordan and all of that. So the first thing that we have here is going to be what we call underdetermined systems. Okay, basically this part that says determined means that you have a unique solution. So something that is underdetermined is going to not work out so well. So if I have 2x1 plus 4x squared minus 2x cubed is equal to, 2x3, those aren't exponents. 2x1 plus 4x2 minus 2x3 is 0. And 3x1 plus 5x2 is equal to 1. This is what we call an undetermined system because there's an insufficient number of equations to match the number of variables. This thing has 3 variables but only 2 equations. So this is going to cause some problems when we work out the Gauss-Jordan thing. So if you think about this, the augmented matrix is 2, 4, negative 2, 0, 3, 5, 0, 1. If you perform Gauss-Jordan on this, and you can go ahead and try that with MATLAB if you want, you get 1, 0, 5, 2, 0, 1, negative 3, negative 1, which is a noisy matrix. It doesn't have that nice, neat Gauss-Jordan ones down the diagonal, zeros everywhere else type form. So this is going to convert back to x1 plus 5x3 is equal to 2, and x2 minus 3x3 is equal to negative 1. But it's kind of helpful because if I get that x3 is t, then x1 has to be 2 minus 5t, and x2 has to be negative 1 plus 3t. So I can write out my solution set of x1, x2, x3 such that x1 is equal to 2 minus 5t, x2 is equal to negative 1 plus 3t, and x3 is equal to t, provided that t is an element of the reals. So that's my solution set. So basically what we've got here is that underdetermined systems are in fact consistent, but they have multiple solutions, right? There's no unique solution. All right, so let's go in the other direction. So here we're going to talk about overdetermined systems. All right, so an overdetermined system would be something like this. x1 minus x2 plus 2x3 is equal to 4. X1 plus x3 is equal to 6. 2x1 minus 3x2 plus 5x3 is equal to 4. And 3x1 plus 2x2 minus x3 is equal to 1. So in this system, we seem to have too many equations. We have 4 equations, but only 3 variables. Now, that's kind of a telltale sign that it might be overdetermined, but it is possible to have too many equations and still come up with a unique solution. We'll get into that a little bit later on in the course as to how you make that judgment. And there's all sorts of tools for that, but let's kind of look at what happens here if we do the Gauss-Jordan thing, because that's usually how you learn what's going on here. So we go 1, negative 1, 2, 4, 1, 0, 1, 6, 2, negative 3, 5, 4, 3, 2, negative 1, 1. And if you do Gauss-Jordan on this, it's going to yield the following matrix. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And that looks like, wow, maybe the solution is just let x sub 4. Well, so there is no x sub 4, so this is the problem, right? So the last line here is the telltale sign. Okay, you have this row that reads 0, 0, 0, 1. If you were to convert that back to a linear equation, you get 0x1 plus 0x2 plus 0x3 is equal to 1. The implication of this would be that 0 is equal to 1, which that's impossible. So this tells me that I have no solution possible to this because there's no way to make 0 equal to 1, which means the system is inconsistent. So a way to think about this is like if this was a set of constraints in an optimization problem, this is overdetermined, meaning that the constraints kind of contradict each other, and there's no way to make all of them happy. Okay, so we're going to throw another term in this that's going to be related but not immediately so, if that makes sense. So hold off and we're going to take a look at that. Okay, so we're going to get into these things that we're going to call homogeneous systems. Okay, so it's a normal system, right? So we're going to have a set of j equals 1 to n, aij, xj is equal to bi, for all I equals 1 to m. Okay, so we have that where b sub I is equal to 0 for all I in this 1 to m. Okay, so this means that you have a system where everything is equal to 0. If this is the case, then you have a homogeneous system. So let's give a quick example of this. x1 minus x2 plus 3x3 is equal to 0. 2x1 plus x2 plus 3x3 is equal to 0. Okay, so theorem. All homogeneous systems have a solution or are consistent. I think it's the way I put it in the notes. Because if you look, if you just make all the variables 0, it solves the system. Okay, so there is a trivial solution. Okay, so like 0, 0, 0 has to solve this system. Now, if the number of equations is less than the number of variables, okay, so this means like we have an underdetermined system, then there are infinitely many solutions. Okay, so that's a pretty straightforward way to look at this. If you look at our example here, we have 2 equations and we have 3 variables and we have a homogeneous system, so we should expect that this has infinitely many solutions. Dig into that a little bit and see if it's in fact true. Okay, so if you take the system that we gave above and you convert it into a matrix, an augmented matrix, you get 1, -1, 3, 0, 2, 1, 3, 0. All right, if we take Gauss-Jordan of that, we end up with 1, 0, 2, 0, 0, 1, -1, 0, right? So remember that this converts back to x1 plus 2x3 is 0, and x2 minus x3 is 0. So if I let x3 equal t, that means x1 is going to be -2t, and x2 will be also just t, right? So, because if these things subtract to give you 0, they have to be equal. Alright, so this means that the solution set x1, x2, x3, such that x1 is equal to negative 2t, x2 is equal to t, and x3 is equal to t, given that t is an element of the real numbers, is the solution set, but there's an infinite number of solutions. So, if I have a homogeneous system of equations, then it will have at least one solution, the trivial solution, zeros, right? And if it is underdetermined, or if the number of variables exceeds the number of equations, I'm going to end up with multiple solutions, an infinite number of them for that matter. Okay, so we're kind of steeping into like some of the finer points of all of this, and we'll get into some of the more efficient ways to be able to figure these things out. But a homogeneous system then is never inconsistent, right? So it's never possible for it to not have a solution. Okay, there we go.